Here's the real reason we care about moments about the x and y axes. So just a quick reminder, if you have a region R that's occupied by some sort of material, and the density of that material is a function of position, so rho is the name for our density function, so it's a function of x and y, then the mass of that region is the integral over R of your density function, dA, and the moment about the y-axis is the integral over the region of x times the density, dA. Everything we're about to say goes just as well if you switch all the x's and y's and work with the mass about the x-axis instead. So the question that we're going to ask is this: at what x-coordinate, x bar, would the region balance on a wire placed along the line x equals x bar? So what we're saying is, right, if we have an x-coordinate here, x bar, if you put it in exactly the right place, this region would balance on a wire positioned along this line. If the wire is a little too far to the right, the region will fall to the left. If the wire is a little too far to the left, the region will fall to the right. But if you put it in exactly the right spot, the region will balance. And we want to know, what is this magic x-coordinate called x bar? The name that physicists give for this x-coordinate is the x-coordinate. So it's the x-coordinate of the center of mass. So that's the key phrase, center of mass. We're going to find the x-coordinate of the center of mass. If you do everything we're about to do, but with x and y reversed, you'll get the y-coordinate of the center of mass. All right, so we're after this x-coordinate, x bar, so that this region would balance on that wire. But balancing, saying that the region would balance, this just means that the moment of R about this line, x equals x bar, should be 0. Because that's what moment measures. Since moment measures the tendency of a region to fall one way or the other, when the moment is 0, it should not fall either way. In other words, it should balance. So all we need to do is determine the x-coordinate about which the region should balance completely. So let's see if we can figure out what that would be. So here's a region R, and here's our x bar. So what we're going to have to do is calculate the moment about x equals x bar. And this is a little bit annoying because this is not the moment about the x-axis or the moment about the y-axis. This is the moment about some different line. So we're going to have to redo our moment calculations, at least to a certain extent. So remember how we figured out the moment at a location x comma y is we took the mass at that location, which is rho x comma y times dA. So this part is the mass at x comma y. And then multiply this by the distance of this point, x comma y, to the axis of the axis that we're measuring the moment about. And the distance of x comma y to the line x equals x bar is x minus x bar. So this x minus x bar is the distance to the axis. So this product gives us the moment just at this single point. Then to get the total moment about the about the line x equals x bar, you just integrate. All right. Well, we don't know what the density function is, and we don't know what r is, so we can't actually make any further progress on explicitly computing this integral. But inside this integrand, we do have this difference right here, and so we can rearrange this integral to take advantage of that difference. It would look like this. Integral over the region of x times rho of xy dA minus integral over the region of x bar times rho x comma y dA. Okay, so this is the moment about the line x equals x bar. But remember, the whole point of the line x equals x bar is that that is where the region is going to balance, and so this moment should be 0. So we'll just set this moment equal to 0. Now this x bar, that's really a constant. And so we can move it outside of its integral, like that. And this first integral, this entire thing, this is the moment about the y-axis. So now we get 0 equals the moment about the y-axis minus x bar times this integral over r of rho times x comma y dA. But that we recognize too. This integral, this remaining double integral, that's just the mass of the entire region R. So now we have moment about the y-axis minus x bar times mass equals 0. And we can solve for x bar. So move x bar times mass to the left, divide both sides by mass, you get x bar is the moment about the y-axis over the mass. Of course, if you do the same thing with x and y interchanged, you get the moment about the you get the y coordinate of the center of mass, and that's going to be the moment about the x-axis divided by mass. So this is really why we care about the moments about x and y, about the x and y axes. I mean, in principle, since the universe doesn't have a preferred coordinate system, it shouldn't really matter what the moment about the coordinate axes are. What you're really looking for is something that's independent of the coordinate system. And the center of mass describes a location in the region itself, or a location relative to the region itself. And the moment about the axes are just a way to figure out where that location is. The moment about the axes on their own don't really tell you anything you want to know. But since they give you, since they let you calculate the center of mass, that's usually why you end up calculating them.